Namaste, we are in week 2 of our course Linear Algebra through Geometry. In the last module, we saw how system of linear equations can be represented in matrix form and what it is to say solving a system of equations. We found that a system of linear equations in 2 or more variables can have only one solution, infinitely many solutions consistent if the system is consistent, or no solutions if inconsistent. In this module, we look at techniques that help us to solve the system of equations when consistent. Let us understand Gaussian elimination. Recall a general system of m linear equations in n variables is expressed as a11 x1 plus a12 x2 plus a1n xn is equal to b1. Similarly, a21 x1 plus a22 x2 plus a2n xn is equal to b2. And the last equation a m1 x1 plus a m2 x2 a m1 x1 xn is equal to bn. This is represented in matrix form. Vector A, vector x and vector b in that matrix form. In the special case of RHS equal to 0, we call it the homogeneous system of linear equations in x1, x2, etc., xn. A solution of the linear system of equations is a set of n numbers, x1 is equal to t1, x2 is equal to t2, etc., xn is equal to tn, that satisfies each of the equations. Let us work out example. 2x1 plus x2 is equal to 3, x1 plus 2x2 is equal to 3. The solution is x1 is equal to 1, x2 is equal to 1. Plugging these values of x1 is equal to 1 and x2 is equal to 1 in the above set of equations, we see the equations in the above system of equations are satisfied. Note, any and every system of linear equations has either 0, 1 or infinitely many solutions, and there are no other possibilities. In this module, we will look at Gaussian elimination technique to obtain the solution, assuming that the system of linear equations is consistent. In order to solve a large system of linear equations, we need a systematic procedure for solving system of linear equations. Consider Ax is equal to b, where A is matrix of coefficients a11, a12, a1n, and the last one am1, am2, amn, and X matrix x1, x2, xn, and the B vector b1, b2, bm. Let us define augmented matrix. Augmented matrix as shown as the matrix obtained by concatenating the columns of B with columns of A. Let us work out an example. The augmented matrix of the following system of equations: x1 plus 2x2 plus 3x3 is equal to 3, 2x1 minus x2 plus x3 is equal to 1, x1 minus x2 plus x3 is equal to 0. I will repeat, x1 plus 2x2 plus 3x3 is equal to 3, 2x1 minus x2 plus x3 is equal to 1, x1 minus x2 plus x3 is equal to 0. So, you see 3 equations with 3 variables. Augmented matrix A B as 1 2 3 3 2 minus 1 1 1 1 minus 1 1 0. Augmenting A with column matrix comes with advantage of making computations manageable. Basic technique for solving system of linear equations is to carry out algebraic operations that do not alter the solution set of the equations, system of equations, and produce successively increasingly simpler systems to that point where one can figure out if the system is consistent or not. If consistent, we also know if it has unique solution or infinitely many solutions. The set of algebraic operations are called elementary row operations. The following are the operations. 1. Interchange any 2 rows, multiplying one row with a non-zero scalar. Third one, adding a scalar multiple of one row with another. Let us go for another example. 2x1 plus 3x2 plus 3 is equal to 6. 2x1 minus x2 plus 2x3 is equal to 3. Second equation. Third equation, 2x1 minus x2 minus x3 is equal to 0. By putting into matrix form, A will be 2 3 1, 2 minus 1 2, 2 minus 1 minus 1, and x unknowns x1 x2 x3. Constant B is 6 3 0. Then the augmented matrix AB is given by 2 3 1 x 6, 2 minus 1 2 3, 2 minus 1 minus 1 0. You see 4 items per row, like that 3 rows are there in this augmented matrix. Swapping and or interchanging R2 with R3 gives 2 3 1 6, and the second one 2 minus 1 minus 1 0, 2 minus 1 2 3. second row and third row has been interchanged. Replacing R3 with R3 minus R2, subtracting third row with the second row gives you 2, 3, 1, 6, 2 minus 1 minus 1 0, 0, 0, 3 and 3. Replacing R2 with R2 is equal to R2 minus R1 gives you 2, 3, 1, 6, 0, minus 4, minus 2, minus 6, 0, 0, 3 and 3. Let us replace R3 with R3 divided by R3. So, 2, 3, 1, 6, 0, minus 4, minus 2, minus 6 and the last one 0, 0, 1, 1. Now we get another system of equations from the original system of equations. They are 2x1 plus 3x2 plus x3 is equal to 6. Second one, minus 4x2 minus 2x3 is equal to minus 6. The last one, x3 is equal to 1. From here we get x3 is equal to 1. The two equations when you solve, minus 4x2 minus 2x3 is equal to minus 6 will result 2x2 plus x3 is equal to 3 and therefore x2 will become 1. 2x1 plus 3x2 plus x3 is equal to 6. So, finally x1 becomes 1. The solution is x1 is equal to 1, x2 is equal to 1, x3 is equal to 1. Let us check if x1 is equal to 1, x2 is equal to 1, x3 is equal to 1 is a solution to the set of equations. If you substitute these values, 2x1 plus 3x2 plus x3 is equal to 6, it becomes 6, it matches. Similarly, 2x1 minus x2 plus 2x3 is equal to 3. So, the answer is again 3. Again 2x1 minus x2 minus x3, if you substitute, answer is 0. We see that the solution to both the systems, namely 2x1 plus 3x2 plus x3 is equal to 6, 2x1 minus x2 plus 2x3 is equal to 3, 2x1 minus x2 minus x3 is equal to 0 and 2x1 plus 3x2 plus x3 is equal to 6, minus 4x2 minus 2x3 is equal to minus 6, x3 is equal to 1 are the same. Such systems of equations for which the solution set is the same are called equivalent systems. Let us take second example. Having two equations with the three variables x1 plus x2 plus x3 is equal to 3, minus x1 minus x2 plus x3 is equal to 1. So, these two equations with three variables, we will put it in matrix form. A is equal to 1 1 1 minus 1 minus 1 1 and x1 x2 x3, constant b is equal to 3 and 1. So, the augmented matrix is concatenating 1 1 3 minus 1 minus 1 1 1. So, solving this with row operations, we get R2 plus R2 is replaced with R2 plus R1, then we get 1 1 1 3 0 0 2 4. R2 is divided by 1 by 2 divided by 2, then it will be 1 1 1 3 0 0 1 2. So, x1 plus x2 plus x3 becomes 3 and 2x3 it becomes 4. So, x3 is 2. Again substituting x1 plus x2 plus x3 is equal to 3, then x1 plus x2 plus 2 is equal to 3, and finally x1 plus x2 is equal to 1. Line with intercepts 1 comma 0 and 0 comma 1. x1 will become 1 minus x2. We can parameterize x2 by assigning any arbitrary value to x2, say t. So, x1 will be 1 minus t. Solution is x1 is equal to 1 minus t and x2 is t and x3 is 2. For different values of t, we get different values of x1. That means this has infinitely many solutions. If you look at example 1 and example 2, before we actually obtain the solution to the system of equations, we terminated the sequence of two row operations at a point where the last row had only one non-zero value in the left hand side of the augmented matrix and one non-zero value on the right hand side of the augmented matrix. We explore this further and define what is called as the reduced row echelon form, abbreviated RREF, of a matrix A. A matrix A is said to be in its reduced row echelon form if it has the following properties. So, first property, if the row does not consist entirely of zeros, then the first non-zero number in the row must be 1. This is called a leading one. Second property, rows that consist entirely of zeros, if any, must be grouped together at the bottom of the matrix. Third property, if any two successive rows, not entirely zeros, the leading one in the lower row must occur farther to the right of the leading one in the above row. Each column that contains a leading one must contain zeros everywhere else in that column. The procedure to obtain the RREF is called Gauss-Jordan elimination method. Let us take an example. Matrix A augmented A 1 0 0 2 0 1 0 3 0 0 1 4. Note, row 1, row 2 and row 3 all have leading ones. There are no rows with all elements equal to 0. Row 2 has leading one to the right of the leading one in row 1. Row 3 has a leading one to the right of the leading one in row 1 and in row 2. All the 3 columns contain leading ones and do not have any other element other than 0. Hence, the matrix A is in reduced row echelon form. Let us take another example. Matrix A, it is 4 by 5 matrix, 1 0 0 2 0 0 0 1 0 3 and output is 2, 0 0 0 all zeros and the output is 0, and the last row all zeros and output is 0. Only row 1 and row 2 have leading ones. The rows containing all zeros are at the bottom. Row 2 has leading 1 to the right of that row 1. The column containing leading ones have zeros in all other places. Hence, matrix A is in RREF form. A matrix for which the first 3 properties hold is said to be in row echelon form. Row echelon form of a matrix is obtained using Gaussian elimination technique. Let us take an example. Matrix A, one, 3, 1, 6, 0, 1, 4, 5, 0, 0, 1, 3 is in row echelon form. Take another matrix B, 4 by 4, 0, 1, 3, 2, 4, 0, 0, 1, 2, 5, 0, 0, 0, 4 zeros and output 0. The last row also 4 zeros and output is 0. This B matrix is in row echelon form. Therefore, the procedure to obtain solutions to a system of linear equations is as follows. Different steps. Step 1. First, what we have to do? Concatenate or append the right hand side column B to the column of matrix A and obtain the augmented matrix. Step 2. Carry out sequence of row operations to obtain the RREF of A. Step 3. Obtain the solution set either by inspection or by converting the linear equation to a parametric form. Some comments on RREF. Let A be an m by n matrix. Consider Ax is equal to 0, the homogeneous system. If the RREF of A has fewer than n leading ones, then Ax is equal to 0 has infinitely many solutions, that is Ax is equal to 0 and it has non-trivial solution. If the RREF of A has exactly n leading ones, then Ax is equal to 0 has only trivial solution. every non-zero matrix has a unique reduced row echelon form. In other words, for every matrix A, there exists exactly one matrix B such that A is row equivalent to B. Fourth, it is easy to verify from the RREF of matrix A if the given system of equations is consistent or not. Let us see the example. 1 0 2 1 0 5. 0 1 3 1 0 3. 0 0 0 0 7. Here we see that the matrix in RREF, however, the row whose elements are all 0 has on the right hand side 7, indicating inconsistency. The last row has zeros, but output is 7. For example, let us revisit our example 2x1 plus 3x2 plus x3 is equal to 6, 2x1 minus x2 plus 2x3 is equal to 3, 2x1 minus x2 minus x3 is equal to 0. The augmented matrix AB 2 3 1 6 2 minus 1 2 3 2 minus 1 minus 1 0. Let us do some row operations here. R2 replaced with R2 minus R1. Then the matrix will 2 3 1 6 0 minus 4 1 minus 3, 2 minus 1 minus 1 0. One more row operations, subtracting row 1 from R3, it becomes 2 3 1 6 0 minus 4 1 minus 3, 0 minus 4 minus 2 minus 6. Again let us subtract row 2 from row 3, then the matrix 2 3 1 6 minus 4 0 minus 4 1 minus 3 0 0 minus 3 minus 3. Then R3 is divided with minus 3, the another operation, then the matrix becomes 2 3 1 6 0 minus 4 1 minus 3. Last row 0 0 1 1. One more operation, subtracting R3 from R2 from R3. The matrix will become 2 3 1 6, 0 minus 4 0 minus 4, 0 0 1 1. R2 is now again divided by minus 4 to get 1. So, it becomes 2 3 1 6, 0 1 0 1, the last row 0 0 1 1. Again R3 is subtracted from R1, then it becomes 2 3 0 5, 0 1 0 1, 0 0 1 1. One more operation, scaling R2 with 3 and subtracting from R1, 2 0 0 2, 0 1 0 1, 0 0 1 1. Now divide the row 1 by 2, then the matrix will be 1 0 0 1, 0 1 0 1, 0 0 1 is 1. So, finally, this is the reduced row echelon form of A, where you can see the variables x1, x2, x3 is equal to 1 1 1. Take another example. 2 having old example 2 having 3 equations 2 equations with 3 variables, x1 plus x2 plus x3 is equal to 3, minus x1 minus x2 plus x3 is equal to 1. Augmenting it, 1 1 1 3, minus 1 minus 1 1 3. Now add row 2 with row 1 replacing with row 2, then 1 1 1 3, 0 0 2 4. Row 2 is now divided by 2, it becomes 1 1 1 3, 0 0 1 2. Subtracting row 2 from R1, matrix will become 1 1 0 1, 0 0 1 is equal to 2. So, the RREF of A is 1 1 0 0 0 1. So, in this we derive that x3 becomes 2, and whereas x1 plus x2 becomes 1, and therefore, x1 is equal to 1 minus x2. The variables corresponding to leading ones in the RREF are called pivot or leading variables. In the above example, x1, x3 are pivot variables. There is no leading one corresponding to x2. x2 is called the free variable. the number of pivot variables is equal to the number of non-zero rows in the RREF of A, that is equal to rank of the matrix A. In example 2, rank of A is 2. In example 3, rank of A is 3. Finally, we can write number of pivot variables plus number of free variables will be equal to number of columns in A. Later we will see the rank nullity theorem, which is another way of stating the above result. Existence of free variables implies infinitely many solutions. To summarize, in this lecture we looked at Gaussian elimination to obtain solutions to Ax is equal to b. We defined the RREF pivot variables and rank of A. In the next lecture, Professor Arul Alan will talk about how the row operation steps actually work and how the solution space does not change. Thank you. Namaste.